So this is module 3.3. We're going to be talking about network modeling in CompuCell. And as always, I need to remind you that this is being recorded and live streamed so that it will be available for people to review later. The module today is going to use a prepackaged program that we've written to make things easier. Hayden sent it around in an email. It's called Tellurium v3. You'll have a zip file. You can also download it from the student materials. And I would ask everyone to please do that now while I'm talking generically about the system. It's going to be critical that you have that running. You will have to have it working on your either desktop or NanoHub installation in order for us to be able to work through this module. And so it's, if people are going to have trouble getting it loaded, it's better to get started now so that everyone has a chance to get it going. Because once we start with it, we're going to be using it for the rest of the session. We're going to be talking about the combination of CompuCell with a new approach to modeling, which we haven't talked about yet much, and which was covered 2 weeks ago for a week by Herbert Sauro in his course. This is going to be the Antimony modeling language. It's a very, very simple way of representing biochemical networks and solving them. And it works in an integrated fashion with CompuCell. Its basic operations are very, very simple, but it also can be made very sophisticated. And so I would encourage you, if you have questions about things that are not covered today or tomorrow, to go to Herbert's reference material. Herbert has a wonderful textbook, Systems Biology, Introductory Pathway Modeling. He has some other textbooks too that are also very good. There are other people who've written good textbooks in the field. The online manual, Tellurium Read the Docs, is great. Has lots of exercises that you can work through. And we've given you the Tellurium Antimony cheat sheet. One thing I should keep saying, which is that you'll see the words Tellurium, Antimony, and SBML used with some degree of interchangeability. In terms of Tellurium and Antimony today, Antimony is the language we're going to use to specify network models. Tellurium is the Python library that executes those models. And so we will be focusing on Antimony today, but I may occasionally drop in Tellurium by mistake. I appreciate your patience with that. In this lecture, we're going to talk about a little bit about the background of biological networks. I'm going to zoom through some slides that are rather complicated, mainly because I want you to have an idea of some of the issues you might face if you're building complex models, and because I want you to have the slides as reference material afterwards. We're not going to be able to go through those slides in detail, and I appreciate your understanding about that. We're going to then talk about how to build network models and solve them in CompuCell. And again, we're going to be using, to begin with, that specific program that we've written that will make it easy for you to do that. We mentioned the other day that there are 4 main kinds of chemical networks that we have to deal with in biology. There are metabolic networks, chemical reaction networks, which tend to be on very fast timescales. There are signaling networks, which operate on slightly slower timescales. There are gene regulatory networks that typically operate on timescales of minutes to hours. And then there are transport networks in the body that can operate on scales from milliseconds to hours as well. You'll notice, if you look in detail at the slide, that the arrows that are used to represent these different networks are different. And one of the things that you'll face if you actually are building quantitative models based on the biology is that you're going to have to do a little bit of interpreting of what those arrows mean. And I'm going to just give you a fly through of that Not enough probably to do it, but enough at least that you might be able to think about some of these problems. The first kind of network that we're going to be dealing with, and the one that Antimony is really designed primarily to address, although it can address all three very well, are chemical reactions. In a chemical reaction, we have a concept of a typical chemical reaction formula. Here, 2-ADP goes reversibly to ATP plus AMP. The typical chemical reaction, we could have something more abstract. 2 molecules of A go to B and back. 2 B goes to 3 molecules of C. C and A combine to form D. And we typically have either unidirectional or bidirectional arrows. Sometimes you'll see multi-headed arrows of various kinds. But the key concept is that you have transformation of mass. The atoms that form atom molecule A are preserved and used to form B, and so on. So a chemical reaction networks preserve mass. And we have always on each arrow the concept of a reaction rate, the rate at which 2 A's are becoming B. And that's the fundamental concept that we're going to be dealing with today. It's a very simple concept. That arrow of transformation is something that we have a pretty good, I think, intuitive understanding of. If I want to do this formally and translate A plus B goes to C from a textbook into a chemical reaction that I can solve computationally, the first thing I have to know is that there is, in fact, a rate law. A plus B goes to C at a rate, VF, that depends on A and B, concentrations of A and B. This will translate into differential equations that describe how the concentration of A, B, and C change in time. You'll notice that this one chemical reaction law generates 3 differential equations, one for each species. If I had 10 species in my reaction, I would have 10 ordinary differential equations. If I'm going to solve this numerically, I have to know what the rate law is. And usually the first assumption, if you're a chemist, is the law of mass action. That is that the rate is proportional to the concentration of A times the concentration of B times a rate. The reason for that is if I don't have any A, I can't be producing C. If I don't have any B, I can't be producing C. And so this better go to 0 when A is 0 or B is 0. If you want to learn more details about this, there are many, many textbooks on the subject. For our purposes, all we need to know is that we're going to be writing arrow diagrams that look like A plus B goes to C with a rate that depends on some variables and parameters in our problem. If we're going to think about signaling networks, what we're going to find is that they look a little bit different. In the first place, they have complex spatial structure because they very often involve sensing molecules, transmembrane proteins like G protein receptors or something else that are bound to the cell membrane, and they send signals inside the cell. And you'll see diagrams like the one at the top. The inputs could be either extracellular concentrations of diffusing molecules, contact between cells, or potentially also molecules that cross the cell membrane and send signals directly inside the cell. Estrogen would be an example of that. You'll see diagrams that look like this as an abstraction of these kinds of networks. This is the famous MAP kinase cascade, where MAP kinase, kinases are things that attach phosphates to other molecules. MAP kinase phosphorylates, attaches a kinase to MAP kinase. MAP kinase, when phosphorylated, attaches a phosphate to MAP kinase, and so on. This kind of arrow diagram begs a question, which is, we know chemically what happens when MAP kinase is transformed into phosphorylated MAP kinase. But what is this vertical arrow doing? That's called a regulatory arrow. And we are going to ask some questions both biologically and mathematically about what to do about those regulatory errors. This is a typical set of questions we might ask biologically about what's going on if we want to understand a problem, because the biology of the modern world will give us concentrations of chemicals. And typically what we need to know is how to connect those concentrations of chemicals to the behaviors of cells that we've been talking about. So you might ask, for example, if there's an increase in the growth factor level in the cell's environment, does the cell proliferate or die? That would be a typical kind of signaling question. If we're talking about mutations, things become more complicated because in general, when you have a mutation, you can't predict what that will do to the rates of reaction. That makes them rather difficult to handle. But it's also possible to ask a question in a more general fashion. If I do a knockout experiment where I get rid of a component or an upregulated component, what happens? Those are a little easier to do than mutations of sequences. Now we have three kinds of arrows. Those arrows are typically written as activators, sometimes with a lollipop, inhibitor usually with a blunt T head, and mass movement or mass transformation with an arrow. You'll sometimes see activation written with an arrow, which is incorrect. People are sloppy. And sometimes you'll see A activates S2, which actually means A promotes the production of S2. And so when you see arrows that look like this, A promotes S2, you're going to have to learn how to interpret that first as a regulatory reaction, and then what it means biochemically, which is nothing goes to S2 with a rate that depends on A. And the fact that it's an activator means that that rate increases. Somebody says they're not seeing the presentation. Is everybody not seeing the presentation, or only one person?
I can see it.
I can see it.
I can see it.
Thank you. It'd be embarrassing to talk for 90 minutes with nothing on the screen. I've done it, I promise. So I appreciate you pointing that out. Okay. For an inhibitor, we have the same thing. We often will see R inhibits S2 written. We have to understand that this means that we don't care what's producing S2, which is why we have nothing going to S2. In reality, of course, something produces S2. But R is controlling a rate. The key difference between a regulatory arrow and a mass transformation arrow is that chemical reactions use up their substrates. They use up the thing on the source side of the arrow. A regulatory reaction doesn't. So that's an important difference. When we talk about gene regulatory networks, there is this complex set of diagrams that try to make gene regulatory networks look actually much simpler than they really are. But you'll see notations that look like this. The questions we will typically ask are, how does the presence of a promoter or a modulator affect the production of messenger RNA for a particular protein? And how does that amount of messenger RNA translate into the production of the protein itself? Typically, those are pretty tricky. And there are a lot of questions that one would like to ask about these kinds of regulatory networks. You'll find that there's a huge literature on the subject. And these really are going to be something that are going to be central to a lot of the kinds of models that people have been discussing. Again, the typical classic notation these days is a picture of the gene to represent the DNA sequence that is encoding the gene, an inhibitor or a promoter that turns that gene on and off, an arrow that represents the production of messenger RNA, and then the transformation of messenger RNA into protein. That, of course, represents the fundamental dogma of biology. This is often shortened by not showing the messenger RNA, something that looks like this. I turns on P, and P is produced. There are a lot of steps in this process. It leads to time delays and various possible post-translational regulation. And so these are things that one has to be aware of. Typically, we'll neglect it. If you want to actually translate that picture, and sometimes it's even shortened to just saying P1 promotes P2, as we saw before, you have to interpret the components. At minimal, for production of proteins, you have two rates, the rate at which the protein is produced and the rate at which the protein is degraded. And classically, one assumes that there is a sigmoidal relationship between the concentration of the promoter and the rate of production of the protein. Those are typically represented by what are called Hill functions. The details of that are somewhat mysterious because typically genes exist in a single copy, so you're either transcribing them or not. And so what is actually happening here is that these continuous rates that you get in these ODE models are representing time averages of stochastically fluctuating rates of production. Gene regulatory networks have typical patterns of motifs. We've seen gene activation. Gene repression would be the inhibitory version of that. The gene is on unless some other protein is present, it turns it off. You can have multiple control, in which case you have to ask how the two factors of control or more factors of control interact with each other. Very often a gene will turn on a gene, a protein will turn on a gene that will make something that turns on another gene. That's a gene cascade. It's pretty common for a gene to turn its own production off or to promote its own production. And it's quite interesting to study the stability and behaviors of networks that have feedback of those kinds. Phosphorylation plays a role, and many other kinds of regulation as well. I mentioned that genes are typically either on or off, but stochastically, CompuCell allows you to simulate Boolean gene regulatory networks using the MabBoss program. The way you do that is pretty similar to what we're going to do here with antimony, but we're not going to be showing that in the class. It's documented, and if people are interested, TJ can tell them more details about how to do that. The third kind, the fourth kind of network that we have to deal with are transport networks. The biggest one that we typically deal with is through the blood. These are typically called physiologically based pharmacokinetic models, but they're really more general transport models. In this case, the body is represented as compartments with blood transporting material from one compartment to another. And the rates of flow can be very fast, for example, in capillaries. If we're representing other transport networks like lymph, the flow rates are slower. But we do have to think about the continual circulation of blood and how that moves molecules around the body. Often we will want to know how, for example, the dose of a drug that we take intravenously or by ingestion leads to a time series of blood concentration, or how the concentration of a molecule in the blood affects the concentration of that molecule in tissue. Mathematically, these kinds of transport models have a simple form. We've heard of Fickian diffusion earlier. Transport has a simple linear relationship, which again has the same form. What's rather nice about all of this is that all of these networks, whether they're gene regulatory networks, metabolic networks, signaling networks, or transport networks, can be written in the form of first order ordinary differential equations. dA by dt, the rate of change of something in time, equals something that's a function of a set of variables and parameters. And that basic structure is something that we'll use over and over again. And any model that can be written in that form can be expressed in the antimony language. Of course, typically these things work together. They don't work in isolation. So we're now going to talk about writing some simple, very simple models. I'm not going to go into complex ones, but fundamentally, what you'd be doing to make complex models is not any different from what we'll do today with simple models. You just have to write more lines, but structurally the models will be the same. And as I mentioned, we're going to be talking about the antimony modeling language. And when you see tellurium, you just have to mentally reserve the word antimony to connect to tellurium. Tellurium is the software that interprets antimony. We're going to write antimony model descriptions. Today, we're going to put them inside of the CompuCell code itself. They could live elsewhere. We can read about models in other ways. When we have them inside of our CompuCell code, CompuCell will then pull them in, turn them into executable code, and solve them with internal libraries. You could run these models as freestanding models independently in Jupyter notebooks or some other Python environment, because Tellurium is a Python library. So you can, in fact, run all of these models as freestanding models as well. Again, I recommend, if you want to read about this more, Tellurium Read the Docs is a great place to start. And the cheat sheet that I asked you to print out is also very useful. So the first thing that we're going to do is write and solve a very simple chemical reaction. About the simplest chemical reaction we could write, we're going to say molecule X turns into one molecule of Y goes back to X. The rate at which X goes to Y is a rate constant B times X. The rate at which Y goes back to X is a rate constant C times Y. This is the law of mass action for a bidirectional reaction. And we're going to load a C+ CompuCell program, the one I asked you to upload. It will run and plot antimony models. We're going to see how to work and define antimony models. We'll run the model. And our simulations are now not going to only have two languages in them, CC3D, ML, and Python. We're going to have three, CC3D, ML, Python, and antimony. Good news is antimony is exceedingly simple. And so that is a plus. I really can teach you in 30 minutes how to write antimony code. So the first thing that I'm going to need you to do now is to upload that model that I asked you to upload. And so I'm going to now switch my screen share to a split screen. And I'm going to do a poll and make sure that everybody was able to get that loaded. It's critical because otherwise we can't go forward today. And so I need to make sure that everybody has that little package loaded. And I'd ask you now to be patient. I'm not going to discuss how that package works. We're going to be focusing on the antimony inside of it and not the CompuCell that is making it work. If anybody needs help getting this loaded, let me know and I can put you, actually, Hayden, I may let you run the meeting and have you move people to a breakout room if they need help.
Sure.
So again, to remind you, we can go to first launch Jupyter on NanoHub. Once you're in Jupyter, select upload. In my case, I've got these things stored in the student materials folder. In your case, you'll have downloaded it and put it somewhere locally where you can get it. And you'll hit upload. In my case, it would overwrite because I've already done the upload. I do need to make sure everybody has that available. If you've already got it up, please remember, switch to CompuCell, launch CompuCell, go to quit it. Sorry, that's showing you the answer already. Go to twit it, and in twit it, open that zip file, unzip it. Don't worry if it throws a warning message. You may have to then open it a second time after it's been unzipped. Looks like I have 18 people who have been able to get it done. I'll give people another minute or two. Again, it's going to be a boring afternoon if you don't have it running, so it's important that everybody have it. If anybody is having trouble getting it up, let me know. Okay, my plan is now, it looks like everybody's got it. I was going to move on. So now is the time to click need more time or raise your hand if you need more time. Good. Okay, so again, you've uploaded it using Jupyter. Now go to NanoHub, open it. Open it here. And again, you'll have it loaded as tellurium v3.zip. Select that. Tell it to unzip it. Ignore any error messages or warnings that it throws. If it doesn't open in tellurium, go back and reopen it. And as usual, you may have to go down one level because it may unzip it inside of itself. So you may have to go inside tellurium v3 to find that CC3D file. So I'm going to wait now to make sure that everybody has tellurium, this file open in twit it. And if you have it open in twit it, you should see something that looks like this. Actually, I better open the correct one because that's a later version. Make sure I have the one. Yeah. Okay. And I'm going to try to minimize the amount of scrolling you see. So I hope everybody has this running now. So again, once you've got it loaded, double click to open it. And then go to Python Steppables here. And at the top, it should open this window here. And so I need everybody to get to where you can see the tellurium. And again, I'm going to ask you to please be patient and ignore the CompuCell part of this. Just look at the orange part here. I'm going to do one more poll and make sure everybody is with me, and then we'll move forward. Okay. If you've got this here, you can go and launch it in Player and see what it does. So I hope people will launch it and see what it does. I'll give you a second to do that yourself before I give you what I get. I get not this. That's my previous simulation. I'm going to get this. And you should see something that looks like that. Okay. So did that work for people? Is there anybody for whom it did not work? What you'll see are two windows. you'll see a blank window because there are no cells in the simulation. And so I can resize my plotting window here, and resize my plotting window here. And what you'll see is a time series of the concentration of my two molecular species, X and Y. And so this is going to then give me, I'm going to time step it rather than running it continuously. It's going to time step those simple law that I've got here. X goes to Y, Y goes to X. Okay. If the time scale that you're seeing is a little bit different, or the size of your dots is a little bit different, you may have loaded a slightly different version of the simulation. I was fine-tuning it till the last minute to try to make it show up as well as possible on the screen for screen shares. If you really want to change things, you can go into the Twidit and edit lines 25 and 36, but I'm not going to go over that unless somebody raises their hand and says they need help with it. We can come back to that later. It doesn't really matter if your dots are a little smaller or if the time scale is a little different, it's going to be the same. Okay. One thing that's available on desktop but will not work on NanoHub is that on desktop you can print and save these plots by right-clicking over the image. If you try to do this in NanoHub, it'll crash because you're not going to have write privileges. But that export option is very useful on the desktop. So just letting people who are using the desktop know about that function. So now I would like everybody to go back to the Twidit menu, and we are going to start looking at Antimony. And the rest of this hour, we're going to spend looking at Antimony together. What you will see here is something labeled equations or rate laws, parameter values, and initial conditions for my variables. And you could go in and try changing the parameter value. For example, if you make C 0.1 instead of 1, always hit save. And now I come back and I run again. And as usual, I have to resize my screen. And now I can see the time evolution when B and C are both 0.1. You'll notice you're going to get a different result. Take a second or two to play with that. If you're ahead of the curve and you could try changing the values of B and C and ask the question, how does the rate at which you get to your final value change with B and C? How do the relative values of X and Y change as you change B and C? And if you've done chemistry and you remember the equilibrium relations for a simple equilibrated bidirectional chemical reaction, you'll know what the answer should be. Okay, so let me make sure that everybody has that, and then we will go forward. Boy, either people are flattering me or this is actually working. I shouldn't say that out loud, should I? Okay, great. So let's come back to our tellurium. Well, let's stay here for 1 second. Okay, so here was our result. And the equilibrium ratio between X and Y after equilibrium is C over B. And if you play around here, you can see that that is in fact observed. So you now have a very simple way of simulating a chemical reaction in CompuCell. And now I'd like to explain how you specify that reaction. Now we're going to go back to our Twidit. And again, these will be in orange. You're going to only have to know about 5 things to be able to build arbitrarily complex biochemical networks. They're only that's why I love antimony. It's very simple. Okay, the first thing is every antimony model is a string. We have here model equals, and triple quotes. Why do we have triple quotes? Triple quotes are Python's way of saying that you're going to have a string with carriage returns. Otherwise, the carriage return new line ends the string. So we're going to say model equals triple quotes and a pair of triple quotes at the end. So our model is just a string. The second thing is that what's inside of it is the Antimony model specification. And that's the Antimony language. And we'll be talking about what that looks like. We have to know that there are comments. Double slash is a comment, and then they added the hash sign to be compatible with Python. So double slash or hash specify a comment. Everything to the right of that is a comment. Like C++, not Python, semicolon specifies breaks between sections. And you can use that instead of a new line character. New line does the same thing. The other thing that you'll see occasionally is a colon, and that specifies one of two things. It can be like in Python, the colon specifies the beginning of a block of function, and we're only going to see that in one context, be tomorrow, or it gives something a name. And so here I have, for example, J1 colon X goes to Y. That's naming the rate law at which X goes to Y. I don't actually have to give it a name. If I do give it a name, J1 is now creating a variable which gives me the rate at which X is turning into Y. So I can then monitor the rate. If I happen to say J1 X goes to Y, J1 Y goes to X, the second one will overwrite the first one. So if you name things, you have to make sure that your names are unique. Antimony was designed to write chemical reactions. And so its primary way of specifying things is in the form of reactions. Here I have to say X goes to Y at a rate Bx. The syntax is almost identical to the way I typed the arrow. J1 colon X arrow, which is minus sign and a caret, Y semicolon, and then my rate law, B times X. This could be, of course, more complicated. 5X plus 7Y goes to 15B plus 10C at a rate B times X times the sine of R squared. Possible. But nevertheless, structurally, name, colon, arrow, semicolon, rate, semicolon. That's all I have to know to write Antimony. Okay, so let's look at this code. I'm writing the chemical reaction X goes to Y at a rate Bx. I write J1 colon, that's the name of the forward rate, X goes to Y, X dash caret Y, semicolon, rate, B times X, semicolon. That's it. This will create two ordinary differential equations, one for X, one for Y. I have here, I'm destroying X at the rate B times X. I'm creating Y at the rate B times X. The second one turns Y into X at a rate C times Y. I'm destroying Y at a rate C times Y. I'm creating Y at a rate C times Y. People very often write network models directly in the form of ordinary differential equations. That's a mistake. It's a fundamental mistake because the arrow diagram that I have here on the top is unambiguous. It tells me exactly what ODEs I need. However, if I write the ordinary differential equations, I cannot, in general, go backwards to infer what the reactions or network were that generated those ODEs. And therefore, it's really important to write things in the form of networks rather than directly as ODEs. And it's a good exercise. You can find papers which have ODE relations written. You cannot infer where they came from. Okay. As I mentioned, naming the rate law gives you access to its current value. And so if I say want the value of J1, that will return B times X. J2 will return C times Y. Okay. I've already talked about the fact that you get two ODEs generated by one rate law. And I'll come back to a little bit of detail in a minute. Antimony requires that anything that's defined as a parameter, like a rate constant B or C, be defined. You have to give it an initial value. They'll throw an error if you don't. It's good practice, although I'm not actually going to follow it here because it's too much typing, to always include the units of your parameters in the comments. You should always say that the units of B are micromolar per minute, micromolar per second, infectious particles per day. You should always include that when you're writing a serious model. Today, because we're dealing with abstract quantities, I'm not going to do that. We also are supposed to specify the initial concentrations of each molecular species. X equals 10, Y equals 0. Antimony will assume that if you don't specify it, that you want 0, but that's risky and I don't recommend it. Sometimes you don't care where things come from or go to. We've seen in regulation, often we'll have nothing goes to A. You can write nothing goes to A. That's a legal thing to do. And that generates the differential equation dA by dt equals rate. Very often we'll have a source with a constant rate of that form. We also heard yesterday and today about first order decay, which is classic. That's sink, A goes to nothing. Of course, in reality, there's always conservation. And usually that goes in a rate that's proportional to the concentration, because we don't want concentration to go negative. So if A is 0, we want the rate to be 0. So we can write nothing goes to A, and that's equivalent to writing dA dt equals K here. Or we can write A goes to nothing, dA by dt equals minus Ka. Somebody caught yesterday that we had a minus sign missing in that decay law in our diffusion. Well, I've just said you shouldn't write ODEs. Antimony allows you to write ODEs. If I write T prime equals rate, beta times T times V, that will generate the single ODE T dt dt equals beta times T times V. That's functionally equivalent to writing nothing goes to T at the same rate. And I'd recommend using that form rather than the top form, if you can possibly do it. If I have multiple rate laws that involve the same species, the rates sum up. Nothing goes to T at a rate K0 creates dt by dt equals K0. T plus V goes to I1, destroys T at the rate here. And so that creates the second term. It also creates the production of I1 over here and the destruction of V here. And so you have to get used a little bit. And if we had more time, I would walk you through in some detail the exercise of translating back and forth between the arrow diagrams and the ODEs. The arrow diagrams are typically more compact for writing things, but the way things are distributed between the lines is a little bit different. It does take a little bit of getting used to understand how to go back and forth. Typically in biology, you have arrow diagrams to start with, and so the arrows are natural. But if you're reading a paper where somebody wrote the ODEs, you have to do a little bit of work to go backwards. Okay, that is all of the syntax that you need to write network models. And so now I'm going to give you an assignment, a very simple assignment, which is take the example that we have here and modify it so that instead of 2 reactions, we have 3. I'm going to rename X and Y to A and B. We're going to rename B to KA. And actually, I think I've got, and so on. And so what I want you to do is write in this equation here, the equation A goes to B at a rate KA times A, B goes to C at a rate KB times C, C goes to D at a rate KC times C. Remember, you'll have to give a value for KA, KB, and KC. Here's some suggestions. We'll have to give initial concentrations for A, B, and C, and D. And the one other thing that you're going to have to do is in line 18, I told you I wouldn't be looking at the Python, but we're going to look at one line of Python. In line 18, I list what I am going to display. And so if I'm going to add a variable, here I have X, and I say I want it in red, and Y in blue. If I'm going to display A, then I have to change X to A. If I'm going to have another species, I don't care about displaying it. I don't have to put it here. But if I wanted to create a species C, and I wanted to display it, I would type comma, quote, C, close quote, colon, quote, color, orange. Okay. So I want people to take the code that we have here and modify it to write A goes to B, B goes to C, C goes to D, and then run it and see what you get. If somebody is ahead of the curve, they can try changing the different rates and seeing how that affects the time series. Okay, is that a clear assignment? Why doesn't everybody take a few minutes to try that? I'll do it as in parallel with you, but try it on your own. It really is pretty simple. And I know saying things are simple doesn't always help when things, if it's not working for you, but really this one, I think, be brave. Don't be afraid. You're not going to break anything. And remember that while cut and paste between chat and Twit doesn't work, you can certainly cut and paste within Twit. So I can copy this line. I want my third reaction here. I can copy that line and put it in. If I do that, remember that I have to change the name of the reaction. If I make that, leave that as J2, it won't work. Said K1. And I should say that like Python, capitalization matters. So if it's lowercase, uppercase, you have to respect that. If you want to use all uppercase or all lowercase, that's fine, but you have to be consistent. people doing? Is anybody stuck? If you're stuck and need help, raise your hand. Again, if you've got it working, try changing the values of Ka, Kb, Kc. You could change the initial concentrations of A, see what happens. There's some rather interesting things that happen if Ka, Kb, and Kc are all 1 versus Ka being 10 times Kb versus 10 times Kc versus Ka being 1/10 of Kb versus 1/10 of Kc. Those three situations give you three fundamentally different kinds of biological process. All of them occur biologically. You can try any parameters you want. You could certainly do a parameter sweep, but I'm not going to get to parameter sweeps today. If you're going to do a parameter sweep of an ODE like this, you're probably better off running the thing separately in Jupyter Notebooks by itself. You certainly can do it in CompuCell, but you've got a lot of machinery in CompuCell that you're not using. Okay. I'm going to go back, try running it. And I got an error. What did I do wrong? Let's see. Invalid syntax. Oh, I have an extra quote. I put 2 quotes in my definition of orange. Make sure everything else is all right. Oh, why? Can't follow my own directions. There we go. That ran a little bit fast, so let me run that again for the parameter values. I'll use the step function so you can see what's going on. Everybody get that to work? Looks like people don't. In this case, I'm actually plotting it with a higher time resolution than what I'm giving you in the base value. Is there anybody who's stuck who couldn't get it to work? Everybody, looks like everybody got it to work. All right. Let me give you a couple of pointers about antimony. I said antimony is very simple, and it is. You can make typos like the ones I made. One thing that you have to be careful of is that antimony has reserved words. Just the way you wouldn't call a variable in Python for. In antimony, you have to be careful. Some of the reserved words are pretty obvious. Time is the time. Don't call a variable time. That's a reserved word. Some things are less obvious. Gamma is the gamma function. And so if you're going to use Greek letters as names, I strongly recommend using something like gamma 1 or delta 1 or pi 1. So you don't run into the fact that you named something, a variable, try to assign a variable name, something that actually is a function. Extra parentheses or improper separators can cause tellurium to die, and it doesn't always die with informative errors. Sometimes tellurium just dies. If that happens, and in the simple examples that we're going to have, it should die with informative errors. But if you have long, complex models, I don't have a beautiful way of doing this, but here's my suggestion. My suggestion is to go through and line by line comment everything out, starting at the top. And the reason you start at the top is that if you're going to make an error, the errors are usually in your rate constant definitions. And so I would suggest going through and commenting everything out line by line, and making sure that the thing runs. And then uncommenting block by block. Initializations are usually quite safe, so uncomment those first. Then uncomment the parameters, and finally uncomment your rate laws, starting at the bottom and going up. And usually you'll discover that there was some missing parenthesis hiding, extra or missing parenthesis hiding in a rate law. It's usually what causes problems. Occasionally what you'll find is that you called something an illegal name like gamma. And again, you'll see that as you go through it. I'm sorry that I don't have a better way of debugging antimony, but after a long experience, that's my best recommendation. So let's try making this just a little bit more complicated then. Your next assignment is to add a single line. B goes back to A. This is now going to be what's called an equilibrium chemical reaction. Our first reaction was an open reaction. Now it's an equilibrated reaction. And the question is, how does your result differ from what you saw before? And again, if you get through this very quickly, you could change your rate constants, A, B, C, or D, or you could change the initial concentrations of A, B, C, and D. If you can do this, you can do anything with antimony, pretty much. It doesn't really get much more complicated. Maybe I should have a poll. Is antimony simple? Okay, so why don't people try this exercise? Somebody asked what the value of KD will be. Pick one.
So why not KD times D, but rather KD times A?
Thank you. That's my mistake. You're very on top of it. Thank you for catching. KD times A wouldn't make sense because the rate of a reaction depends on the things on the left-hand side, not on the right. Thank you very much. You'll notice in the first case, this is the one that I had before. Eventually, all of my A, B, and C are turned into D. Everything turns into D in that open reaction. Now, when I go back and run the new one, I'll see that I equilibrate. And I get a fixed amount with fixed ratios of A, B, C, and D. I don't get only one. So this is a classic equilibrated chemical reaction. Did people get that? Maybe a show of hands. How many people got something that looked like that? If you pick different values for Ka, Kb, Kc, Kd, you'll get different ratios of the amounts. Is it okay to move on, or does people need more time? Raise your hand if you need a little more time. Okay, so here I've taken screenshots. In the right-hand case is the open reaction. Everything becomes D. In the left-hand one, I've actually used Ka equal to 1, Kb equal 1, Kc equal 1, Kd equal 1, in which case I get equal amounts of all of them. Why don't I go back and do that? You can do that with me. Let all my rate constants be 1. I'm going to go back. Run it again. Everything comes to the same point. I can't do the chemistry really here. There's a lot of interesting chemistry to do. Okay, I can write more complicated reactions. And one nice thing about antimony is that it knows what's called stoichiometry. If I have 3 molecules of A plus 5 of B combining to make 1 of A again, plus 2 of C and 9 of D, and I type that exactly as it's written, it will work. It will keep track of the counts of how many molecules of A are created and destroyed, how many B's and C's. That's another great advantage of the arrow diagrams compared to using the ODEs, where I have to keep track of all of those stoichiometric coefficients by hand. So that's one of the big strengths is complex chemical reactions. So why don't we try that? Why don't you actually write something like this? Maybe this one will take too long to type, but give it a shot. 3A plus 5B goes to A plus 2C plus 7D, and so on. The last one you'll notice is D goes to nothing. That's a decay reaction. Tell you what, just write the first line of this. Let's not do all of it. I don't have quite enough time to do it. Well, maybe. Only take you 2 minutes. So I have 3A plus 5B goes to A plus 2C plus 7D. And my rate law is Ka times A. One thing you have to know is the up caret is the exponentiator in antimony, not the double star. So that one is a little bit of an antimony annoyance. A cubed times B to the 5th. The second one I had was 2A plus 2D goes to 3E, and the rate is KD times A squared times B squared. The next one was 3E goes to 2A plus 2D, and the rate was KE times E cubed. Third one was D goes to nothing at the rate KD times D. You can set all the K's to 1 if you like. One thing I have to watch out for is Ka. I've got Kd. I've got Ke. Now I'm using instead of Kc here, and I need to give an initial value for E. And I'm not going to plot E. I'm going to just leave it off like that. Okay. Try that, see if it runs. I must have made a mistake, not doing anything. But, oh, I know why. Why is this doing nothing? Somebody who's a chemist, tell me why this is doing nothing. E equals 0, yes. This reaction is not going to occur because I don't have any B to start with. So let's start with some B, C, D, and E. So something interesting. So now I get my reaction. Okay. You can, if you didn't catch up, do all of that with me, you can try it as a homework assignment. Okay, that really was the last thing I had for today. So we can maybe play around a little bit more. I wanted to get us done by 6. So I went through things a little bit quickly. But you've got the basic antimony syntax now. So I hope that was useful for you. Next time, what we'll do is we'll talk about a few other things that you can do with antimony. You have something called events, which allow you to change parameter values during execution. Of course, you can do that from Python too. You can solve the differential equations also stochastically using something called the Gillespie algorithm. I'll show you how to do that. And then there are a couple of details about the way antimony interprets things that we need to know. And then the next thing that we're going to do is actually look at how the Python code works. How do we actually load sorry, I shouldn't really scroll this way. How do we load an antimony model? How do we plot it? And how do we manipulate it from CompuCell? So that's what we're going to do next time. Okay, so questions. I'm going to put up, why don't people play around a little bit with this in the parameter values while we're talking? What's the method it uses to solve the ODEs? There are a number of choices that you have. It uses standard C-vote integrators. And so you can choose which one you want. Occasionally, you'll find a situation where you'll get a divergence error. That's very unusual, but it can happen. But normally, you don't need to worry about what integrators you use. Any other questions? A question about reaction diffusion equations. I'm sorry, I missed that. So there was a statement about that the species can diffuse. So here you can write reaction diffusion equations, but you write reaction diffusion equations in CompuCell using the diffusion solver. So those are specified in the XML. And that has some limitations. There are limits to how complex those functions can be. Alternatively, what we're doing here is we're going to be writing ODEs inside individual cells. There was a function in CompuCell called advection diffusion that actually did the PD solution that AJ is asking about. I'm not sure that works anymore. Nobody used it. One of the problems that we face with CompuCell is people ask for interesting functionality. We write it and then nobody uses it, and then it gets lost as time goes on. But what we will do next time is we will see how to couple ODEs between cells. We can do that either by contact or you can do what was suggested, which was shown earlier today, which is you can have cells secrete and absorb from their environment. So you do diffusion as a field, and you do the reactions inside of the cells using antimony. And that typically is the most efficient way of doing these kinds of computations. And very often it is what happens. There certainly are situations where cells secrete chemicals and the chemicals react outside of the cell. But most of the complex biochemistry is happening inside of the cells. And so to simplify that into a network isn't a bad approximation. Other questions? Did everybody get their complex chemical reaction to work?
We do have, so Rana, would you mind screen sharing for a second to show us what's happening? Oh, she said she thinks she got it. So Sarana was
Okay.
getting an error saying no SBML element exists for symbol X, even though she had no X variables in her model.
Right. That's because you were asking it to plot the value of X from the SBML. And so here in this line 24, if I ask it to plot a variable that doesn't exist, that will throw an error.
Gotcha.
In fact, I made precisely that mistake myself when I first did it. So you're going to see in the breakout sessions, you're going to see lots of models that do exactly what you want. I don't know if we're going to get to do one of those in the regular class because they get to be a little bit complicated. But we could definitely, during the hackathon, we could take half an hour and write one together. It's pretty straightforward. If I have a concentration A of a chemical, then I can have my cell secrete at a rate that's proportional to A. And so that works pretty well. The one thing that I do have to do is I have to do the mass balance by hand when I do absorption and secretion between antimony and the field. I don't get that for free. Any other? I don't know. We should probably have a demo like that. The viral infection and immune response model that I showed as a CompuCell model on NanoHub, that uses that method. So the virus is produced by cells and secreted into the environment. The virus binds to the cell and is endocytosed. And so that's an example where you have the subcellular viral replication model coupled to the viral field outside the cell. So that would be a demo with that. The disadvantage of that model is it's quite complicated. So you have to do some digging inside the code to find the part of it that's doing the thing that you're interested in. But that's a good suggestion to have. 2 years ago in 2020, we taught this course entirely around viral replication and infection. And actually the demos from the 2020 course would cover that pretty well.